we talk about contrapositive, but in order to understand that, we have to go through some basics in set theory. And set theory is like grouping things together and find out the relation between them. There's a relation is like a necessary condition and sufficient condition. Some of them is a necessary sufficient condition. For example, if you are a human, you eat. Okay, what you're saying is, if you are human, you are part of the human, and human belongs to eat group. So if you are part of a human, because human belongs to eat group, so you eat. Okay, this is correct. Contrapositive is, if you don't eat, you deny this, then you aren't a human. Okay, we use this notation to show you are the element of human and you are also element of eat group. Okay, there are some definition and axiomatic statement always to construct math. We start with those axiomatic statement and construct a theorem, right? So there are two statements. Subset 1 belongs to subset 2. Subset 2 belongs to subset 3. Then subset 1 belongs to subset 3. This is like, this belongs to this, this belongs to this, then this belongs to this, right? We don't need the proof for that. Now, second one is subset 1 belongs to subset 3 and subset 2 doesn't belong to subset 3. Okay, then subset 2 doesn't belong to subset 1. It's no relation. Okay, we don't need the proof for that. Now, we talk about converse, inverse, and contrapositive of the statement. Okay, statement is either true or false. If x is greater than 2 is true, then x is 3. This is not correct because it's greater than 2, it can be 4. The 4, x is 3, it doesn't. But this is a necessary condition, right? X has to be greater than 2 because x is 3. Okay, we have another necessary condition here. If x is smaller than 4, we cannot say then x is 3. That's not correct. But x has to be smaller than 4 because x is 3, right? Another necessary condition, if x is integer, we cannot say x is 3. There are many integers. Okay, so those are necessary conditions. No matter how many necessary conditions you bring up, it doesn't prove x is 3. But let's consider the converse. Converse, if x is 3, then x is greater than 2. That's correct. If x is 3, then x is smaller than 4. That's correct. If x is integer, then no, x is 3, then x is integer. That's correct too. So you have a relationship here saying necessary condition is false. Sufficient condition is true. Okay, so necessary condition converse is sufficient condition. We examine this. X is integer. Suppose this is a real number and this is integer, and x is greater than 2 is this one, and x is smaller than 4 is this one. So 3 sit right in the middle. Okay, so if you say x is greater than 2 and smaller than 4 and integer, then we're talking about this area, right on 3, right? So if we bring all of them together, it's become sufficient condition. So we can say this and this and this is gonna be sufficient to say this. Okay, now let's consider inverse. Okay, necessary condition x is greater than 2. If x is not greater than 2, x is not 3. That's correct. Well, you deny everything above 2, so x cannot be 3. That's correct. So inverse of necessary condition is true. Okay, the same thing here. X is not integer, then x is not 3. That's correct. But inverse of sufficient condition, x is 3, then x is not integer. Well, you cannot say that, because x is 3, x is not 3, the x could be 4. So sufficient conditions inverse is false, right? And necessary condition and sufficient conditions are converse relationship. One side is necessary, one side is sufficient. And inverse change the statement true and false. Now, contrapositive means, okay, if x is greater than 2, x is 3, necessary condition. Contrapositive is you deny conclusion first and see if original statement can be denied. Okay, so x is not 3, then x is not greater than 2. And we're talking about converse of this sufficient condition is inverse of necessary condition. So it's true, statement true. But contrapositive, necessary conditions contrapositive is sufficient condition and inverse, so it's false. So contrapositive depend on who you start with, necessary condition or sufficient condition. It can be true or false. But if you put all together with and, then it's become same equivalent statement, which means necessary sufficient condition. Okay, so it's all become true. So necessary become sufficient, and it's all become true because they are identical. Okay, now let's try if we combine this together with and you say x is not true, x is not 3, then how do you deny 3 and? So we need a De Morgan's theorem here. Okay, this is A, this is B, this statement C. A and B and C, we deny that. It's the same as denying A or denying B or denying C. Okay, what it does is, okay, this is A, let's change the color. This is A, and we deny that. No, A and B and C, right? And it's only this area. You deny that means everywhere else. Which is same as denying A. We denying A and denying B and denying C. So remaining is only this part. So De Morgan's theorem is obviously correct using Venn diagram. Venn diagram shows De Morgan's theorem is correct. So in the statement x is not 3 is same thing as saying x is not greater than 2. Is that true? Okay, so you deny one of them and become or, so that's sufficient. If denying is correct, then remaining doesn't matter. It can be correct for others, but or is basically plus. If this is 1 logic equation, remaining is 0, still 1. Okay, so that's the contrapositive. What is the use of contrapositive? In the math, you often use proof by a contradiction. Prove that A is false. Okay, to do that, suppose A is true, then B. But this is a contradiction. Since B is not true, then A should be not true. Okay, so using contrapositive to prove this, but we have to be careful here. Example, okay, square root of 2 is a rational number, p over q, ratio of the integer. Okay, then we come up with even number equals odd number. Since even number and odd number is not same, so we deny the claim square root of 2 is rational number. Okay, but this could be sufficient condition for saying this. Okay, well, if necessary sufficient condition, you can say this. But if this is just a necessary condition to be this, then you cannot claim contrapositive is correct. So you cannot say this. So this proof has to be such a way that this is a sufficient condition to claim this, right? And necessary sufficient condition. Because otherwise the contrapositive is not correct. Here, remember? Sufficient condition, the other way is necessary condition and inverse. Sufficient condition, inverse is true. Okay, so this sufficient condition is good enough. Sorry, sufficient condition to say, then this way should be correct. So we can deny this claim. Okay, that's the proof by a contradiction. So when you prove this, this has to be sufficient condition to claim this, right? Then you can say, if this is not, then this is not. Then you have to look at each other, say, either one is wrong. This is wrong or this is wrong, right? Because this claim is contrapositive of this claim. So either one is wrong. But this is obviously wrong, so this is denied. Okay? That's the proof by a contradiction. So we have other interesting videos. Please check it out. I hope you enjoyed listening to this.